A ball is projected horizontally down a ramp, inclined at angle alpha. Assuming the impact at A1 is elastic, that's the first bounce, and ignoring air resistance, find the distance to A2. I got this nice little problem off of Walter Lewin's YouTube channel. He does a similar problem of the week, and this one was a two-part problem where first you find A1 and then you find A2. We'll do both today. This is an interesting one because as the diagram shows and gives a hint of, it's best to tilt your axes because you're trying to find the distance from the origin, where the projectile begins being a projectile, to the distance A2, which is down the ramp. So if you set your axis down the ramp, that makes it nice and tidy for finding that distance. You're only finding the x component of position. So first, it might be useful to kind of redraw the situation for yourself, where this is the ramp, making that the x-axis. This is then the y-axis. Here's the negative y-axis. And there's some initial velocity here. And that would make gravity acting at 90 degrees from that, right? This is the angle alpha that we're given, making this also the angle alpha. And this is going to fly to point A1 here, and then bounce. And if you can imagine in your head, a very hard ball perhaps bouncing against a very hard ramp, impacting elastically, then it's going to cover a longer distance in the second bounce and subsequent bounces than in the initial bounce. And you might be able to picture it in your head, ping, 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 and it's dropping, dropping, dropping faster because it's being accelerated by gravity. So it's covering a larger distance each time. So since we're taking non-standard axes, we can't use our typical projectile motion equations, which are pre-baked in with a couple different choices when they're derived and presented in most textbooks. One is that you take your origin at the moment or the place that the projectile begins being a projectile, which we have done here. But the other more important one is that the y-axis, must point in the positive upwards direction, which is the opposite direction as gravity. That way you get your projectile motion equations, which is like, for example, y is equal to v naught sine alpha t minus 1/2 gt squared, right? And then you only have your acceleration in the y direction. Well, we can't do that because we have acceleration components pointing along the y and the x because we've tilted our axes. So we have to rederive the equations. So up here, the equations I've listed here are given for just standard kinematic equations. And we can use that second equation there to find the position x and y given our choice of axes and our initial velocity incline here, alpha. So x at any time t is equal to, we have x naught being 0, so we can leave that out, v naught, but here we have just the x component is what we're looking for, so cosine alpha times t plus 1/2. This is the component of gravity that points in the x direction, so g sine alpha t squared. For the y, we again have a initial y position of 0, and we have v naught sine t, alpha t, minus, because the y component of gravity points in the negative y direction, 1/2 g cosine alpha t squared, right? So there's our position projectile motion equations tailored to this new situation. And if we just take a time derivative of this, alternatively, we can think about this first equation and think term by term what's happening. but we could just take a time derivative. So dx dt would give us our x component of velocity at any time t. So that would be v naught cosine alpha plus g sine alpha t. You can see this is not looking like our standard projectile motion problems. Equations, dt is equal to vy, which is v naught sine alpha minus g cosine alpha t, right? So the 2 comes down, annihilates the half. All right, so here are our equations that we get to use. And now what ultimately the problem wants to know is the distance to A2. But we can see that we kind of have 2 projectile situations. We have the projection of the ball to A1, and then we have some sort of elastic situation that's going to happen here. Let me redraw that. Whoops. Right here. And then we have, after that elastic collision, then we have another projectile motion problem to do to find A2. And since we've placed our axis along the direction of the distance that we're trying to find, that makes it nice and convenient. So first, we're just going to handle this first projectile motion problem. So we're going to call this A1 here the end of our first problem, right? We're going to find the first distance here, A1. And to do that, we have to think about what's true. What do we know at point A1? Well, what we know is that the y component of position is 0 because the ball is impacting with the surface of the ramp. So at that point of impact, y is 0. So looking at this equation here, y is 0, and we have v naught sine alpha t minus 1/2 g cosine alpha t squared. And from this, we can find the time that the ball impacts at A1, use that time to plug in for the x, and then we found the distance to A1, right? So this gives 2 results. T is equal to 0, which would be at the origin. That's also true. The math don't lie. But also, it gives t equals, right? You can pull out a t from each one, and then you're solving a small little equation. This is like the subset from the quadratic formula with the c coefficient plugged in as 0, which is the form that this takes. There's a quadratic with the 0th order term being 0. So the shorthand is just kind of thinking about pulling a t out and then solving what's left inside the parentheses. So we have v naught sine alpha over, and that would have a 2 up there, g cosine alpha. More simply, 2 v naught over g times tangent of alpha. All right, so that's our t. So now we take that t and we plug it in for both the locations in the x position equation. So x at point A1 specifically, because this is t at point A1, and well, that's the origin. So this is t at point A1 right here. Let me write that better. So x at A1, we're saying is v naught cosine alpha times this junk we're plugging in, 2 v naught over g tangent alpha, plus our other term, 1/2 g sine alpha times our value for t squared, because the t is squared there, right? All right, so now let's see if we can clean this up a bit and get a more reasonable result for this. So we have, every time I place my palm down, it changes the zoom on the screen there. Sorry about that. So we have 2 v naught squared over g, and we have cosine alpha. Oh, the g's, no, G's do not cancel. So G stays. Cosine alpha times tangent of alpha. And if tangent is sine over cosine, then you have just sine here. So that cleans up kind of nicely. And then the second term, we have tangent squared, which gives us a lot of stuff here. In fact, we can just, that's 3 sines, so we're just going to leave tangent as tangent. One of the 2's cancels, but the other one does not. So we have 2 v naught squared. One of the g's cancels, but not the other one, over g times sine alpha. And then we have a tangent squared alpha. And this looks kind of nice because they have a whole bunch of stuff that's the same in both. So really we have x at point A1 being equal to 2 v naught squared over g sine alpha times 1 plus tangent squared alpha. And in fact, 1 plus tangent squared alpha is a trig identity, and that is equal to 1 over cosine squared. So let's just say xa1 is equal to 2 v naught squared sine alpha over g cosine squared alpha, right? So that's pretty tidy. We can turn one of those into tangent if we want, I suppose, but maybe we just leave that for now. I don't think it's any simpler to write. All right, so this is the exposition. The exposition, it's like we're in a courtroom. This is the exposition right here at A1, right? So we just found that. And so now we have a second projectile motion problem, right? And we keep in mind that if we place a new origin, and I'll do a new color here, if we place a new origin here, right? And this will be some angle, and we have some initial velocity here for our new projectile motion problem, then we will have to add on the initial displacement from the origin to A1 to whatever final position A2 that pops out of our new projectile motion problem. The fact that this projects or that it impacts elastically means that it does not lose any of its y component of velocity as it bounces. So you can think of it as merely reflecting. So the final velocity from the first one, so this would be like VA1 we can find, that just reflects up to become V naught for the second one, right? V naught, we can label it as like V naught 2, right? So that's the interesting thing. So it doesn't, and then whatever x component of velocity that existed also, doesn't there's no friction or anything. It just, it impacts elastically, so it's the same there. All right, so that's the key for the impact. So now we have a new projectile motion problem, but in order to find this new initial V naught, which was, by the way, right, if we were to apply the same process, crucial in knowing, we could just write it down because the actual V naught was given, but our V naught 2, is not necessarily the same, right? And so, and in fact, it won't be because we have an x component of gravity here, right? And so it's going to be changing a little bit, and that's why it's taking a longer and longer time, or covering a longer and longer distance, rather, per bounce, right? So we have to find Vx and Vy in order to proceed, or at least we have to find one of them, right? We at least have to find one of them. So let's go ahead and find Vx. So here, this is still our first problem. So the V at A1. So Vx A1 is what we want, right? Vx A1. So let's look up here to our equation. We're looking at this guy. So that's equal to V naught cosine alpha plus G sine alpha times t. And so if we want that final velocity at point A1, we have to plug in the time that occurs. So we're plugging in this time here. So I'm going to get rid of that arrow and say we're plugging in this time here now into that equation up there for this t, right? Okay. So let's do that. So we have 2 V naught tangent alpha over G. And we're plugging that in for t to the first power, so we're safe leaving that with no exponent. All right, so let's see. So this is as simple as it gets, V naught cosine alpha. But over here, we get our G's canceling, which is nice. And we have 2 V naught sine alpha tangent alpha. All right. And that I don't think can be simplified in any kind of way. So that is what it is. So this is Vx(a1), which is also, by the way, equal to Vx naught 2, or however you want to list it, right? V naught x, V naught 2x, or whatever, right? So it's the x component of the initial velocity for that second projectile motion problem that we were thinking about in green, right? All right, so if we go through and find, again, the time to A2, now we're thinking about green, time to A2, we want to know the time that this occurs, right? We want to know the time that occurs. We have a new projectile motion equation or problem here, and we can find the time that occurs. So now we're going to say the y, I'm going to get rid of my little sloppy things. We're looking at this guy here. The y is 0 at A2, and we have a new V naught to work with, and we're going to find the time that occurs, right? So here we go. So y, which is 0, is equal to, looking up here, this guy, y is equal to, see if I can fit it all in there. Nope. We have a new V naught, so we have to plug in our V. Oh, well, we don't have a full V naught here, right? We just have the x component is what we have found. But if we can find the y component, then we have this entire dealio here, right? So if we have the y component, then we have actually that whole thing there, right? So let's find that y component. Let's go back and find that y component. And maybe you're already looking at or thinking ahead and realizing something, but I think I'm committed at this point to finding it explicitly. So we have Vy A1. So this is the y component of velocity at A1. And what we are saying is that the final y component velocity at A1 can be found via now this equation, right? And we're working with our, like, you know, what we're thinking of as like part 1 of this problem. So V naught y, that's what we're trying to find at A1, at time A1 we're going to plug in, is equal to V naught sine alpha, V naught sine alpha, minus, looking at this guy, right, minus G cosine alpha times t. And here's where we plug in our t for A1, which maybe I should have made more clear here, but that's this guy. equals TA1, right? That's not the final result there, but that's a useful one. All right, so we have times 2v0 tangent alpha over g, right? Okay, so here we go. Can this simplify? Not too wonderfully. So we say Vy(a1) equals v0 sine alpha minus 2v0 over g. Did I lose my g? I lost my g. Minus g cosine alpha there. So then the g's cancel, as they should, because that's what happened in the other one as well. And it's a symmetric thing here. So 2v0, we don't have an over g, cosine alpha tangent alpha, right? Okay. So there we go. So here, we are saying that this is equal to the initial y component of velocity for our second problem, right? And what we're thinking here about the elasticity is that it reflects. It reflects, right? And so whatever the y component of velocity was for the final A1 is the inverse of the initial, because it reflects across that that x-axis. And so this becomes the inverse, right? So we're going to say equals negative v0, negative y, vy naught 2, to stick with my same convention, right? Because it reflects. And if it reflects, you might be able to convince yourself without going through finding the magnitude of the overall magnitude, right? That would be kind of silly, the overall magnitude. And then plugging it into here. Or maybe we can just go forth with taking just the y component like we were going to. All right, oops, I wanted that line. So we're looking at this equation. Maybe you spot what I'm kind of hinting at here, that this can be done a little bit simply by noticing some symmetry, which is always very helpful. But let's say we don't have that intuition working for us. We haven't figured it out yet. Let's go ahead and plug that in, right? Let's go ahead and plug that in. So here, this would be for the y component of the initial velocity. But we have that here, except for, it's the negative. So we have that when we do this. We have that. This entire thing here is the y component of the initial velocity for our new projectile motion problem, right? So we can plug all that in and then just tack on a t, right? And that gets us what we want, okay? So we have so what we were doing over here. The y position is 0 when it impacts at A1, which is the same point as for the initial for this new problem, right? So for let's see, what are we doing? No, we want at A2 rather. That's what I had said here. So we want the time at A2. Excuse me. So this is now beginning really in earnest, A2. So the y position is 0 at A2, right? And so we can say y, looking here, 0 is equal to, maybe I zoom out a little bit, give us more view. And then instead of v0 sine alpha, which is just the y component of the initial velocity, we're going to write all this junk that I've boxed in green, right? So we have, I'll switch the order, 2v0 cosine alpha tangent alpha minus v naught sine alpha times t. And then we have this term that's left over here. So minus 1/2 g cosine minus 1/2 g cosine of alpha times t squared. Just t squared. And what we're trying to find here is want t at a2, right? So we're back to everything that we know. We know alpha and we know v naught, like the actual just v naught, not v naught 2 in this equation. And the only thing that we have as an unknown is t, right? So t is going to be equal to 0. That's going to be t at a1, by the way. And t at a2 is going to be, is going to be 2 v naught cosine alpha tangent alpha minus v naught sine alpha divided by this 1/2 g cosine alpha, because we would have pulled the t out, and then you bring this guy over, and then you divide that guy, right? Okay. All right. So let's see what happens here. So does this simplify? Because this is looking like garbage, right? So we have a 4 here, because the 2 goes up top for that first term. 4 v naught cosine over cosine, so this goes away. Tangent alpha minus, we have a 2 v naught, and let's see, and we have a g under here, g, 2 v naught over g, and we have a sine over cosine, so that's tangent alpha. Did I do this correctly? I believe so. So then what is 4 of something minus 2 of something? It's 2 of something, right? So the time at a2 is equal to 2 v naught over g times tangent of alpha. Look at how beautifully this cleaned up, right? Do you notice anything about this? Do you recognize anything here? Let's compare this to the time at a1. 2 times v naught over g times tangent of alpha. 2 times v naught over g times tangent of alpha. It's the same, right? So that's a big insight to this problem that you may have already spotted up ahead. That's what my kind of hinting and maybe a little bit of reluctancy to go all the way to prove it along the way over the past few minutes has been. Because if you kind of imagine a ball falling down a ramp, right, if there's no air resistance and it's impacting elastically, the time is going to be periodic. It's just covering a larger distance down the ramp and speeding up, right? But it's not because it's shorter and shorter time or longer and longer time. It's because the distance, that the velocity is increasing because it's being accelerated. But it's the same time to impact, which is really interesting. And also kind of gives us an exciting opportunity to think about the distance to n number of impacts down the ramp, right? If that's periodic, we can think about that. Okay, so now we have the time at impact A2, right? So now we have everything we need. We have the initial x and y component of velocity. All that we need is this. So now I'm going to erase my reference there. Now we need this equation with the initial x component of velocity in place of this junk. And we need to plug in our time, which is the same that we just found. 2 times v naught over g times tangent of alpha. All right, so that's the game plan. So we can go now to x at point A2 is equal to, this part is the x component of velocity, v naught 2, and that is here. So we're going to plug that in. So v naught cosine alpha plus 2 v naught sine alpha tangent alpha. Looking back up to the problem, there's a t left attached to that parameter, so we put t. And then, did I capture everything? Yes, I did. All right. And then we come up here and we see plus 1/2 g sine alpha t squared. So plus 1/2 g sine, let me make double sure here, sine alpha t squared. Oh, but we wanted to plug in our t. We can do that in the next step. It's enough to keep straight here. So now we're going to plug in our t. So I'll just label this A2, and we'll expand this to plug in our t. So we have v naught cosine alpha plus 2 v naught sine alpha tangent alpha times 2 v naught over g times tangent of alpha. And then let's give a nice healthy end parentheses there, plus 1/2 g sine alpha times 2 v naught over g tangent alpha, and that t is squared. Hoo boy, these are a lot of trig functions, right? Does anything clean up? Well, let's just expand it out and see what we got, right? Let's just see what we got. So we're gonna distribute this first term. So we're gonna have 2 v naught squared cosine alpha tangent alpha over, I'll put the g out front, over g, plus 4 v naught squared sine alpha tangent alpha, or tangent squared alpha, and there's a g on that term as well. Okay, some similarities there, but not completely the same. Plus 1/2, oh, these g's, one of the g's cancels. So I'll just do this guy. And 1/2, oh, let's see. So there's a 2 up there, so it's not going to be a half. There's going to be a 2 up top. We have a v naught squared over g. Oop, this is looking nice. We have a sine alpha, and we have a tangent squared alpha. Let's see here. Double checking to make sure I've done my distribution here right. Okay, so that's looking good to me, right? That's looking pretty good. So then if we tidy this up, what can we pull out here? What is similar, what is not similar? Let's see, these two terms are almost the same, right? These two terms are almost the same. So that's like a 3 thing. So I'm just gonna, I'm just making sure they are exactly the same. Yes, so if we have 4 plus 2, and that gives me, instead of a 4 there, it's going to be a 6, because we add 2 more of those same dealios, and boom, there we go. All right. And let's see here. Is there anything else we can do to clean this up? Well, before we clean this up too far, let's remember that this is just really this isn't really xa2, to be honest. This is just delta x for the second journey. So I should really change this to like delta x2, right? Because this is the green treats this as our origin, but we have the original displacement to tack on here, which was this one, right? So let's bring that in here. And maybe it's cleaned up too much because look, maybe this one would be better. In fact, let's bring it in that form because that clearly looks to match more of what we've got going on, right? So let's see if I can squeak in here just a little bit more room. And I'm going to bring in this form down here, adding on to this whole stuff, right? So because what I'm saying is the distance xa2 is equal to xa1 plus what I've now labeled delta x2, right? So therefore, and I've used up a line doing that, but therefore we have xa2 being equal to 2v0 squared over g sine alpha plus 2v0 squared over g sine alpha tangent squared alpha. Okay. Let's see. Oh, hey, look. Looking up at this original term, I'll just continue writing it out. So plus 2v0 squared over g. So now we're referencing just here. So I'm going to go back to this. So look at cosine alpha times tangent alpha. That's sine alpha, which matches this term. So that's pretty freaking nifty. And then plus 6v0 squared over g sine alpha tangent squared alpha. All right, so look at what we've got. We've got some things that combine. 2 of something plus 2 of something is 4 of something. So 4v0 squared over g sine alpha plus 2 of something plus 6 of something is 8 of something. So I'm going to write plus 8v0 squared over g sine alpha tangent squared alpha. And we get to pull some stuff out. We get to pull out a 4v0 squared over g times sine of alpha. That's a lot of stuff to be able to pull out. That is very satisfying. And that is times 1 plus 2 tangent squared alpha. And here, I believe, is where we end. I don't think that simplifies anymore. So that is the distance to A2, right? And if you look at how that differs or compares to the distance to A1, it might give you some hints as to what changes from one to the next, right? Right? So this guy got multiplied by 2 for the second bounce, right? And for the first bounce, you can think of like a multiplier of 1. And then this guy got multiplied by 2 for a second bounce. Whereas up here, you can think of a multiplier as just 1. So here, without any extra work, just understanding the periodicity of the time being the same for each one, we can now just write down for n number of bounces, we have 2n v0 squared over g times sine of alpha times 1 plus n tangent squared alpha. And isn't that just gorgeous? Gorgeous. What a cool problem, right? What a cool problem. So non-standard projectile motion axes causing non-standard projectile motion equations, which we solve for from our original kinematic equations. Really just one if we thought about taking the time derivative, right? And so therefore, we found the distance to the first, and then thought about the elastic reflection of the final velocities becoming the new velocities directly for that second journey. And then realized that solving the rigorous way, saying that the y component of the position for that second A2 bounce is going to be 0 again. Then we solve for t with an even more complex initial velocity for an initial y component of velocity, and found that that t simplified to the same dang thing as it was for the first interval, which is a big insight to the problem if you catch that before you have to rigorously solve all of that. And then we took that t and plugged it in for the final x position for that distance from A1 to A2. And then we tacked on also the distance from the origin to A1, and it's simplified so beautifully. And then just noticing from one to the next, we got our n number of bounces equation. All right, if you liked this problem and you want to see me continue doing this, let me know. And I'm going to try to find more interesting problems and present them to you, because I have a lot of fun solving these sometimes. All right, I hope you have a great rest of your day.